Maybe you take the attendance at the end, ma. Emma?
Okay, sir.
Yeah. So let me present. Then I will. So hope my screen is visible to everyone. It's appearing in your screen. So yesterday I forwarded a video related to the method called Actrex method. It's a abbreviation. It is in abbreviation form, ACRREX, where A stands for, as I indicated in the slide, that abstracting. C stands for categorizing, R for reflecting, and reformulating, then extending. So this method is a particular one important method in bioinspiration that we will look at multi-inspirations. That is, you look at different inspirations in the nature, then you collect different points and different knowledge from that as per whatever we discussed, the principle of causality, something like that. Then we are going to form many solutions for a single problem, many possible solutions for a single problem. That's the reason why. So in this particular method, once you develop a technology or once you develop a solution for a particular problem, then you can extend to any other similar problems. So that is the advantage we have in this particular method. Okay. So this Actrex method, especially these all words you must have heard about, that abstracting, categorizing, reflecting, reformulating, and extending. I always emphasize on the point that the biomimicry is not bioinspiration. The bioinspiration has more freedom to think. Bioinspiration has more degree of freedom to work out. So that is reflected in this particular method in the fourth point, that is reformulating. Okay, it is not only abstracting, it is reformulating. That means if you find something is better in this using the same method or using the same approach or using the same inspiration, if you think you can actually uh, develop the develop it further, or if you think you can enhance the effect further with some ideas, then that is called reformulating. Okay, which I said in your concept document. If you see in the concept document, I presented it as the here you see making into an engineering problem. So that is called a reformulating. So reformulation is always like we are actually thinking whether we can enhance or applying our own ideas to the inspiration to reformulate it or to develop it further. So this way, abstracting, categorizing, reflecting, reformulating, and extending are all stand for the different parts of the or different processes in this particular method. So abstracting means what? So abstracting generally look at when you look at something, when you look at in that video you must have seen, you will look at different objects like this. So different objects like this. So in this, actually you find the event is going on. That means the cub may be holding to the mother, or mother is holding the cub. So in all cases, that is the case. Okay, but That is what you are looking at. That is not what you are looking at. What you are looking at is what is the common point in this one. So you can you abstract some device which can do the same function. So that is where you have a crocodile clip, you have a different kind of clips these days. Because abstracting is, I wrote there, if it is main sense is a conceptual process where general rules and concepts are derived from the usage and classification of specific examples. That means these are all examples. That means you are going to gain some thought, you are going to gain some idea from a particular inspiration. So that is called abstraction. So how you are going to gain the idea in that video I clearly explained. So that is the reason why when you look at some inspiration, different people think about it in a different way. Different people get different thoughts. Different people get different ideas. That's why we kept it as abstraction. Abstraction is always different for different people. That means when you look at something, how your thoughts and ideas are going on. So that is what actually abstraction means. Then based on whatever the common points you find in that particular event, whatever the common points you find in the different inspirations, you are going to categorize accordingly. That's what I did here. So I categorize them according to the phenomena where entity A is holding B, entity or entity B is holded by entity A. So if I take object 1 and object 2, in one case object 2 is holding to object A, in other case, object A is holding the object B. So this is what the classification means. That means when you look at multiple inspirations, if you find some common point among them, you are going to categorize them into a particular. You are going to classify them, or you are going to separate according to the particular point. That may be a function, that may be a behavior, that may be a form, that may be an event, whatever I'm saying it as. Here it is the function that is holding. Okay. So next case also same thing, but these are not, these are the different kind of things. So here also same thing. It's a holding. One is holding the other. But point is common. You can't say this is different as far as bio inspiration is concerned. You can't say these events are different to that of this event. So as far as clipping is concerned, as far as holding is concerned, all are same. You cannot categorize them as different one. So all come under single category. This is called classification. Okay, I am looking at something, I'm getting some information, I'm getting some idea about it, about the function or the behavior or the form, anything. With respect to that idea, I'm classifying different inspiration. Here, with respect to the function called A is holding B or B is holded by A. Okay, so based on that idea, I classified all these inspirations into single category. That is called categorization. So once the categorization is over, you are going to reflect on it. That means how reflection is generally done. You are going to look at what are the different things in common you are going to observe in these things and how your inspirations are going to work. So that is what you are going to look at. So when you think that your inspirations, all inspirations are giving different information, definitely you can combine them and come up with some idea. You can come up with some solution. Okay, this is all creating new ideas or new forms or new functions or new behaviors. So this is the way we take multi-inspiration, but we take the uh, idea, that means the common idea which is existing in all these things, then we get a different information, then based on that understanding we are going to build something. You will see in the example. Okay, based on what I understood from this and this, which I'm saying is classified into a single category, categorized into a single one. I'm saying these are all same, following the same function. One is holding other. Okay. So in this particular case, I would like to apply that particular knowledge which I got from multi-inspiration. All the information from different inspirations I got. So using that information, using that understanding, can I actually apply on this particular thing? This is the device. What is this? So plug and socket. So in this plug and socket system, can you apply that idea so that you can actually make a, because now these days it became a very important thing now. All e-vehicles are coming. So that time, 2 years back, we thought like that to apply on this. And I'm happy to say that one student, I think he is your senior, he realized this. He applied the bio-inspiration in the case of the electrical vehicle plug, and he realized it. Okay, so that is the way multi-inspiration, especially Actrex method, we are going to use. We see the common point in many inspirations and get all the informations and collate them, understand them, assimilate them, then apply onto a particular application. So that is what the categorization, and after that reflection. So reflection is always like how I'm going to use this information, what this information actually giving me, what kind of understanding it is giving me, how can I apply it on my problem or the process. Then reformulation is always, as I told you before, reformulation, the certain changes which you want to bring to improve it. Okay, so to improve it, if certain changes, if you want to bring in the system which you derived from this inspiration, that you can always give, that is called a reformulation. So that is what exactly we are doing in Actrex method. First of all, look at multiple inspirations and take the common point, categorize them, then understand the different informations related to that common point from all inspirations, then you assimilate them, understand them, then apply onto a single system. Once you apply that one with some reformulation, then you can extend that to different technologies. You need not to stick with only plug. The same idea you can extend to different areas. Okay, different areas, different domains, and different designs. That is briefly about the Actrex method. So Actrex method is mostly based on the multiple inspiration and observation of the single function or single form or single event, single form and single behavior in multiple inspirations. You are always looking at a common behavior and you are categorize them according to that commonality. So that commonality information from every information you are from every inspiration you are going to get that commonality information. The once you get that, then you are going to apply to your problem or to create the solution. Then after once you develop one technology, that won't allow you to stay calm because it is always provoke you. You apply the same knowledge in different place. That will always happen. That's why extension will always come naturally. Once you understand that in depth, that will naturally come to extend to different places. Okay, so that examples here and there we will see many times. So that is about the Actrex method. So now I request people to, if you have any questions, you can ask. Otherwise, I request Preetham to present his screen. So Preetham is my PhD student. As far as in our laboratory, in the bird laboratory, we developed a technology or a system by using multi-inspiration. Of course, a slight differences or a slight new things we introduced. Those are we named as multi-inspirational designs for additive manufacturing, MIDAM. Okay, so the name is not that good. Okay, don't worry. So that is for additive manufacturing. We specially proposed that method. But in that, what you need to observe is how he derived inspirations into forms and how he realized a system. So that is what most important, because Actrex method is not the method which you sit and do. It is always experimental. It is always experimental. How you are realizing it is most important, because you are creating a new knowledge by observing different inspirations and the common point in different inspirations. So that knowledge is very precious. So that's the reason why. So he will present the whatever the concept he developed, the multi-inspirational designs for additive manufacturing. Because that 3D printing, all those things are very important these days, right? So that is for additive manufacturing. So that method he is going to present, and the rest of the time he will present and we will listen. Okay. Here the main important theme is how he got the different inspiration from different inspirations, how he assimilated them, and how he applied to a particular problem and realized a system. That full story he will present. So thank you very much. Please over to Preetham.
Thank you, sir.
Yeah.
Am I audible?
Yes, you are audible.
Good morning, students. So I'll be speaking about multi-inspirational design for additively manufacturable products. So this work include collaboration by 3 people, me and your senior Kopakar and sir. So together we designed this system. So by multi-inspirational design, what I mean is multiple bio-inspiration. Okay, so it's not just inspiration from a single being or plant or something like that. It's from multiple natural sources we incorporate into the system. And additively manufacturable product is basically we are resorting to 3D printing, fuse deposition modeling, 3D printing, which is very conventional 3D printing technique. And the device which we intend to make is actually fully 3D printable, right? So we'll move on to the first slide. So I'll start with the introduction, what basically we did. So we combined bio-inspiration with additive manufacturing for developing a device we call it, which is called a spin coater. So first I will tell you what is spin coater. So spin coater is a device, you can see a substrate. So you want to coat a thin layer of some material onto the substrate. So this spin coater will allow you to do that. So the basic principle of operation is you will drop a liquid which you want to coat over the surface, and there is a mechanism on which you will place this substrate and it will start spinning after dropping your solution. So due to centrifugal force, it spreads away from the center, and a uniform film is deposited based on the RPM of rotation and time of rotation, acceleration, all those parameters are there, which you need to optimize for getting different thickness of the this fluid onto this surface. So this is basics about the instrument. So to develop this, we considered bio-inspiration along with additive manufacturing. So why bio-inspiration? So we all know that whatever we see in nature, whatever is surviving till now, it has endured millions of years of evolution. So the reason they are surviving till now itself is because of the evolutionary advantage they have got over others, and which couldn't survive, they actually perished and became extinct. So nature can be like a never-ending source of inspiration for developing products. There are different ways which you may already know of incorporating bio into system. So generally we categorize it as bio-inspiration, biomimicry, and bio-integration. So in case of bio-inspiration, you already know you will not strictly follow copying of this biology into your system. You will just study its functional behavior, mechanism, designs, and you are free to incorporate whichever aspect of that biological system into your device or system. And next is biomimicry, that is exactly copying the biology into your system. And next one is biointegration. So in this biointegration, basically you will take some maybe an being and like some bacteria and integrate into your system. So that is biointegration. So we used bioinspiration. So we studied the functional aspects and design aspects of a biological being and incorporated into our system. Then we what is additive manufacturing? So here we use fused deposition modeling. So this is a very conventional 3D printing approach, easily available. You may also be aware of that. So advantages of 3D printing are like you can do rapid prototyping. You just design it in your software and you can directly 3D print whatever structure you want. In case of subtractive manufacturing, you have a lot of headache on how will you machine those unwanted parts. But in case of 3D printing, you can just simply design and just print. So that allows more flexibility towards approaching bioinspiration, right? Because bioinspiration may involve very complicated structure, and additive manufacturing allows us to freely incorporate it into our system. And yeah, complicated natural structure can be easily copied to get a bio-inspired design. So I can just, in a nutshell, I can say that bio-inspired design assisted additive manufacturability appears to be potential topic for research in industry perspective. So you will know why it's a potential topic in industry perspective, especially Indian industry, because you may see that most of the Indian devices. So, okay, I will talk about spin coater itself. So these are some of the spin coaters. Most of them are manufactured in India, and you can just look any other spin coater as well. You can see very conventional design like cylinder or some very primitive geometry of cuboid all over the design, right? There is no curves, no better aesthetics which goes into the system. Yeah, you may argue that this is a scientific instrument and why we need some design perspective to it. But thing is, as a customer, when you buy something, you won't just look at the functional, you will look at the beauty as well. So it is one of the unique selling point which you also have to consider while designing a product. So we can't simply neglect just because these devices work, so we need not think about the beauty of it. So these are functional, no doubt about that. And one more aspect to consider is these are very costly devices. This spin coater which we have in our lab is costing almost 70 to 80,000, and though it's functional, but it looks so boring. And thing is, by incorporating bio-inspiration to these devices, you can improve the functional and design aspects, as well as you may sometimes reduce the cost as well. So I will go through the process flow for multi-inspirational design modeling. So first thing which we have to do is the parts and parameters which are crucial for targeted instrument, you have to study that. Okay, so as sir in the previous example, he showed socket, electrical plug and socket and switches. So you know what you want to do, basically what all the aspects and parameter of the system you have, and you want to build. So you should be very much clear about it. So you have to chart out that. So in case of spin coater, we have body casing, that is whole structure body, and a spin drum. Here you can see this is the drum within which this whole mechanism of spinning is incorporated. So some casing is required. So next is chuck, sample chuck, basically substrate, where you will hold the substrate. The base alignment screw, the alignment of this whole instrument is very important, because when you drop a fluid, so if the alignment is not good, it won't stay in the center. It will go towards the side which is inclining downwards. So it will cause a non-uniform coating over the substrate. So you want a lid, because a spinning substrate will spill the fluid everywhere. So you need a lid with the hole for solution dispensing. That is when you are dropping Sometimes you have to drop a fluid when the substrate is rotating at high speed. So what happens is if you simply drop it, it will spill over you. So you need some opening for dropping the liquid over the lid itself, and that opening should be exactly at the center of the substrate. Okay. Then you need a motor, electronics, and what is the size of the electronics and motor, the space it will take, the display unit, user interface. You have to consider all that. And at the last but not the end, since we have a motor that is a something which is in motion, definitely there will be some vibration. So we have to consider vibration isolators as well, because this will be useful in good uniformity and reproducibility of the results for thickness measurement of the films. So next is so different scenarios you can imagine. So you know the problem, you know the parts, you know the parameters. Now different scenarios, combining them. So where you basically want to place your different parts and parts which you need. So again, you have to chart that out. So we recognize all these things. That is, we know the proper alignment of sections. Display should be properly placed in strategic location. You have to align motors, and you have to align sensors around it, so that you can get the measurement of RPM. You have to know the strategic locations of vibration isolation, because you can't simply place the isolators where there is no vibration. So because you want dampening to happen in the locations where higher vibration is there. Then strategic fastening points, and basically this is a modular design, right? So you need a proper location of adding fastening bolts, and solution channelization. Basically you will drop a solution over substrate, right? So it should it should be free to flow outwards. Otherwise at the end of the substrate there won't be uniform coating. Then expulsion and ease of detachment, all these are just in basically you should understand these are all the engineering aspect of your system. So you are basically in and out about your system. Okay, so next this is the core of MIDAM, that you have to create a analogy matrix with each requirement, and charting the multi-inspirational system. I'll go to next slide, which will give you better understanding. So you just already charted out what are the requirements: body casing, spin drum, and chuck holder, alignment screw, and all those things. So you can chart it out in one column. Then suitable bio-inspirational analogy you will list out. So for each requirement or sections, I considered two inspiration, and whichever inspiration I found it better in terms of functional aspects, I considered them. So like that, you have to chart out your bio inspiration in this form of table. So let's start with the first one, body casing. So what I know about body casing, so it is a body casing basically holds the whole structure of the system. You want it to hold the user interface, the motors, electronics, and all the functional parts of the device. So it should have a good structure to hold everything. So looking at the bio inspiration, I think you already know some websites where you can look for bio inspiration. Obviously, we are not staying in like jungle that you will visit a rainforest and look for bio inspiration around you. So you have to resort to website or things like that to look what is the research that has happened on biological beings and all those things. So we resorted to Ask Nature. So we looked like what all suitable structure for holding the all the components, that is body casing. So tortoise and starfish, we found it as the most suitable one. So among these two, functional perspective. So these look good in terms of aesthetic as well. You can see a star structure is more aesthetically pleasing, but again we found that the tortoise has more volume to incorporate all the functional parts at the center. So we chose tortoise over starfish because of that reason, as well as tortoise has a very low center of gravity. It is very nearer to the ground, and this structure facilitates our need. So that is why we chose tortoise. So next we'll go to spin drum is basically it comes along with the body casing. So we consider tortoise already, so I didn't chart out the suitable analogy for that. So next, moving on to sample check. So the need of sample check is basically to hold the substrate, which is spinning at a very high speed. Okay, so and another one important thing about chuck should be that it shouldn't block the fluid which we drop over that. So it should freely expel the excess fluid which is sitting on top of substrate. So while it's spinning, otherwise what will happen is fluid won't be expelled, and at the edges of the sample holder you will get a thicker film. So we don't want that. We need a uniform film, right? So excess fluid should be easily ejected out of the substrate. So for that, what we need is some channel we need over the substrate holder. So we looked into nature where we see such kind of channels. So we saw that there are some leaves like Pandanus fosteri leaf. So this is actually a plant in rainforest where rainwater which falls over this leaf get channeled through this center channel, and it goes into the roots. Okay, this curvy nature basically facilitates the flow of water to its roots. So this we consider. And another aspect, another leaf which we saw is Aurelia leaf. So this is actually based on the hydrophobicity of the this leaf. In terms of like fabrication, this is more simpler because we can just simply 3D print the channel and incorporate it into substrate holder. But in the case of the second analogy, we saw that we have to use some hydrophobic coating over the substrate holder such that it allows the flow of excess fluid from top of the leaf. In case of Aurelia leaf, why such type of hydrophobicity is there? In order to keep the leaf wet free and easy flow of the liquid, as well as to avoid dust collection. So next is base alignment screw. We didn't think of any suitable analogy for that. So next we'll move on to a lid with whole solution channelization. And then next one is, as I told, there should be lid with some opening to allow the drop of solution, right? So how can we make it look better? Shall we just put a lid with a hole, or shall we make it aesthetically pleasing as well? So we looked again for a bio inspiration for that. So this flower, you can see it has some this structure. So we found it very aesthetically pleasing, so we incorporated into it. And but we can also consider a mushroom as well, mushroom shape over the lid. I know some of you may be confused what I'm speaking, but once you see the design, you will understand what I'm speaking about. So these mushroom design is what we have to do. We have to make a lid and make a tube kind of structure to allow the flow of solution. But so we didn't find it much good one because it's difficult to clean this channel. But this is an open channel, right? Like so this is easier to clean the lid. So we chose this one. And next one is vibration isolation. So we found two suitable analogies, that is octopus suckers, that is this one you see. You may find this very often in your shelf where you are holding hooks. Holding hooks will have this suckers. And then you have a woodpecker skull bone. You already know, right? Woodpeckers are having a skull bone which allows it to be safe from concussion when it is repeatedly hitting over the wood. So it protects its brain from any damage. So we observed that its bone has a porous structure. So we resorted to some porous structure which is easily available. Yellow sponge. So we took it as a bio-inspiration from the woodpecker to reduce the vibration isolation, as well as a low-cost approach it is. So this sponge is easily available. This is basically a packing material. So you basically charted out a suitable analogy for the sections and requirements. Okay, so the most frequently asked question is how you know which is suitable for a system. So there is no clear answer for that. There is clear answer in the sense there is nothing like right or wrong answer. It's only best answer. So it should be based on your decision, which is suitable for you for designing as well as 3D printing. Here we are talking about additive manufacturing, right? So I will talk about ease of manufacturing by 3D printing. If it is some other manufacturing technique, so you have to look for are you able to manufacture that this design onto that technique. So such all things come into picture when you are designing. So there is no right or wrong answer. It's just like a best answer. So as a designer, you have to think about it by charting out the function and ease of manufacturing, all those things. So next, moving on to next two steps. So additive manufacturability analysis of the multi-inspirational system. So you have chosen the suitable analogy, and then you have to manufacture it by 3D printing, right? So what you have to do is certain aspects of 3D printing you have to consider while manufacturing. That is size of the model to 3D print. Is it too big for your 3D printer? Can you really 3D print? That factor you have to consider. Then splitting big symmetric structure into smaller printable parts. So imagine the whole structure itself is too big. Is it symmetric such that you can divide it into equal individual parts so that individually you can 3D print for a smaller 3D printer? And scope for reduction of support structure. So as a designer, you always need to reduce the wastage, because more wastage means more cost of the overall product. So you will try to reduce it by reducing the support structure in terms of 3D printing. How will you strategically place it over 3D print build plate so that you get less support structure? I hope you know support structure. Support structure is basically supports automatically generated for 3D printed parts. Those supports actually are like for the part of the part where it is hanging. So there is no consecutive support for it in the model. So the software will automatically generate supports for that. So you can, if you don't know, you can just have a read about it. And so how will you reduce it? So you have to think that aspect, and then design. Then the next step will move on to design, modeling, and 3D printing. This is just a software part where you will just model it according to all the parameters you consider. So this can be extended again to any type of manufacturing technique. So if it is sheet metal, you can consider all the aspect. Can you bend the material the way you want, all those aspects. So you have to think about the manufacturing aspects as well. So this is more flexible. So I just talked about additive manufacturing. So as I was saying, how can I reduce the support structure? So if I had placed this in a, this is actually a panel for display and numeric keypad. So if I had placed in another way, you would have got support structure to hold this this surface. So we found that by placing in this way, we can reduce the support structure. Things like that you have to think for additive manufacturing, and to optimize the design for 3D printing, you have to think about that. And so yeah, so this is the drum which I was talking about. And I know this whole design may not make sense to you now, because I was talking about tortoise and all those things. You can't see tortoise here, but after assembly you will see the real picture. But you can see one flower design here which I was talking about. So it has a center uh, deep well which allows the channel flow. So you can see it here. So this is the lid with that central hole which allows the flow of fluid. I am printing in this way to get a better print quality. And one more fact I talked about additive manufacturing, that is how will you divide a big structure into smaller symmetric structure. So this is actually a feat of the spin coater, which was actually a symmetric four-sided part. So we divided into four smaller units to print it consecutively, and later we combine it by using some fastening screws or glues. Yeah. So this is the whole body casing which allows the storage of all the electronic components. It is a post for motor, spinning motor over this. So this is the final design structure. So now I hope it resembles a bit like a tortoise. So this is the head, these are the feet of tortoise, and this is the whole shell of the tortoise. Okay, so here you can see this is the chuck which is holding the substrate. So whichever all the bio inspiration which I was talking about earlier, you can see here. First one is tortoise. The whole structure is in the shape of tortoise. As we are considering bio inspiration, we need not copy exactly. We are just aesthetically or functionally copying the nature of the structure. So this is about tortoise. Then leaf, which I was talking about. So you can see the channels right here. So these channels allow the easy flow of excess fluid. So when I drop liquid at the center, so here you can't see the substrate, I didn't include it. Substrate is actually a glass slide of 2 by 2 centimeter. And when you drop a fluid over it, it should flow out because this is spinning, right? So these channels allow it for easy flow. That was from a leaf which is normally found in rainforest. And then we talked about vibration isolators. So here this is a vibration isolation shoe which will incorporate this sponge, which is a porous structure. So as I told, this vibration isolator should be placed strategically throughout the structure. So we place it on the foot as well as near this display and control panel, so that the overall vibration doesn't get transmitted to the table and your whole table doesn't start vibrating. So this is the lid which I talked about. This is inspired by a flower which has a deep groove at the center, and this is actually at the center of this substrate, right? So if I place over this drum, it will be very much self-centered. So if you pour a liquid over this, so it will just fall over the substrate exactly at the center, allowing you to not worry about the centering of the fluid. So you will get a uniform coating. So this is the control panel with display. So next important step, which as an engineer you have to consider, is the testing of the requirements. So did all this aspect which you considered till now, till here, did it hold well? So if it doesn't hold well, you will go back and reiterate the analogy matrix for each requirement, or whichever requirement is giving you problems, and you will improve it. So it's like a loop here. So I'll just go into the requirement aspect. The display unit and the numeric keypad which I showed earlier allows us to enter certain values. Okay, so which will correspond to RPM. Okay, RPM of spin on the chuck. So we saw that as we increase the input constant, RPM also increases linearly. And one of the interesting thing about the device which we encountered while testing is above 4000 RPM, there is a resonant regime. Do you know? I hope you know resonance. So every device has some natural frequency of vibration. When you vibrate that instrument at that frequency, the vibration gets amplified due to the resonance, a phenomenon called resonance. So there will be a huge vibration which will be observed above 4000 RPM. That is speed of rotation of the motor. So we had to reduce it. So what we thought is incorporating extra this sponge all over the places, strategic places, such that you can further reduce the vibration. So here I placed accelerometer onto different position on the device and recorded their amplitude for a specific amount of time. If you apply a Fourier transform to that signal, you will get certain peaks. So these peaks will correspond to certain frequencies of amplitude which is repeated. So this frequency will give you the vibration, cyclic vibration which you will observe in your device. Okay, so we saw at 4000, above 4000 RPM, this frequency of vibration that is around okay, at this point above 50. So just consider it as 75 hertz. So this vibration is having very high amplitude, and when we reduce, that frequency is reducing, as well as the intensity of that vibration is reducing. You can see, right? So as the RPM is reducing, and so to reduce that vibration amplitude, we incorporated. So this is without vibration. So same image, same graph. So now with vibration isolation shoe. So one thing I want to tell you, this vibration isolation shoe, though I showed you in the beginning, it was not actually considered in the beginning. So we just designed the model as it is without vibration isolation. We didn't consider it. So you may also encounter such kind of things. So we had to go again back to charting the analogy matrix to add this vibration isolation shoe. So we saw that when we add this vibration isolation shoe, from the amplitude of vibration from 4800, it got reduced to 1600. So so this vibration isolation shoe is working. So to reduce it further, to reduce the higher frequency vibrations, we added extra dampers. That is the sponge we incorporated near the motors, so that less amount of vibration get transmitted to the body. So it actually suppressed a lot of high frequency vibration around the device. So basically it's working. So in conclusion, I would like to say is MIDAM framework is applied, we applied to the spin coater as a case study. So this is just to understand how multi-inspirational design we can apply to system. So this was a very simple system and very straightforward multi-inspirational design you can consider. But in case of complex system, there will be more things you have to consider. Next is the application of method resulted in additively manufacturable, low cost and affordable spin coater. So we reduce the support structure by considering different aspects of additive manufacturing, and there was a scope for tunable resonance of vibration, which is facilitated by considering multi-inspirational design. When we were working, so we saw a lot of vibration, right? So the structure of the starters allowed us to add more vibration isolation sponge around the device to reduce the further vibration. And this works basically shows the possibility of exploiting the bio-inspired design to support additive manufacturing of different products. So thank you. You are welcome to ask any questions which you have.
Yeah. Any questions you can ask? Before that, I would like to indicate one thing is this design which he Krupakar along Pritham and came up with, actually facilitating that vibration dampers. It is not like that we are creating something extra and for vibration dampers. It is facilitating to keep these dampers. So that is the speciality we observed. Now you saw quantitatively that how it reduced. It published as a chapter. You can read that. Uh, I think he's sharing again. Now, if you see some more dampers, actually you can incorporate here at this position. Oh, okay. Yeah.
At
So
the
yeah, there. Shoe
image.
you can anyway. He mentioned at the same time that void regions also you can actually put the vibration dampers. So that is going to make this design really versatile as far as vibration isolation is concerned, and also as far as spin coater price is concerned. So that kind of things we can achieve from multi-inspiration. This is one example. So tomorrow I'm actually requesting one more person, Mr. Sahil Bandare. So he developed that electrical plug system. So if he accept, I think he accept that, I will keep that class tomorrow, because these are the two successful methods. Last two successful products came up from multi-inspirational systems. Otherwise, tomorrow we will sit and do the assignment in the class time on multi-inspiration uh, concept development. Okay, so that is about the MIDAM. And if you have any questions, you can ask Preeta.
So if you want to read about this article, you can just Google this title. The paper is openly available in forum like ResearchGate. Okay, just read more about it.
This also published as I think chapter, book chapter.
Yeah, yeah. There is a conference proceeding for International Conference on Research on Design, which was conducted in IIT Bombay. So their proceeding name is Design for Tomorrow. So in that it got published.
Yes. So why we are presenting this is because this is very closely related to the Actrex method, and this is the example that we can realize products using this kind of methodology. Yes. So if you have any questions, you can ask. Or yes, thanks, Preetham.
Thank you, sir.
Yeah. Then tomorrow we will meet to do some assignment on this one. So there itself you have to submit by the end of the class, maybe within a half an hour after the class. So with that we can complete this first method called Actrex method. Okay. So Jay Pratap, can you stop the recording?
Yes, sir.
Why I'm asking these people to present, because that will give some